Lay down now, make yourself comfortable, close your eyes, and take a deep breath. Let your body sink into the bed. Let your mind drift gently and prepare to travel to a place far beyond ordinary experience. Tonight, we will explore the very beginning, the moment before everything as we know it began. Don't miss a night of fresh documentaries. Hit subscribe and share your location in the comments. What's the time in your corner of the world? All right, one more quick question before we begin. What existed before the Big Bang? We often think of time as always moving forward, a line that stretches endlessly in both directions. But when scientists look at the universe, they find that time itself has a starting point. When we talk about the Big Bang, we are not just talking about the explosion of matter or energy. We are talking about the beginning of space, time, and reality as we experience them. Before the Big Bang, the familiar concepts of yesterday, tomorrow, and even now may have had no meaning. Space and time were not yet unfolded, and the universe as we know it did not exist. This is the first challenge of understanding what happened before the Big Bang. Our tools for thinking about the world are based on time and space. To imagine a time without time is to step beyond everyday experience. Scientists have long used mathematics and physics to explore this puzzle. The equations of general relativity, which describe how gravity shapes the universe, suggest that if we trace the history of the cosmos backward, we reach a point where density and temperature become infinite. This point is called a singularity. At a singularity, the laws of physics as we know them break down. Space itself becomes compressed to nothing, and time stops in its usual sense. Classical physics cannot tell us what came before this moment. Yet the singularity is not the end of the story. It is an indication that our understanding needs to include quantum effects, the strange behaviors that dominate the very small, where particles flicker in and out of existence and uncertainty rules. Even though we cannot look directly at the universe before the Big Bang, we can see the echoes of its earliest moments in the universe we can observe. The oldest light we can detect is called the cosmic microwave background, or CMB. This light was released about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and photons could travel freely. The CMB is a snapshot of the young universe, frozen in time, and it carries tiny variations in temperature and density. These variations are like a map of the earliest structures, showing how the universe expanded and grew. By studying the CMB, scientists can infer what the universe was like in its first moments, and even test ideas about what might have existed before it. Another important clue comes from the motion of galaxies. Scientists observed that distant galaxies are moving away from us, and the farther they are, the faster they recede. This discovery led to the idea that space itself is expanding. If we imagine rewinding this expansion, the galaxies would get closer, together, until all matter and energy were packed into a tiny, extremely hot and dense state. This is the essence of the Big Bang theory. The universe was once very small, and everything we see today has expanded from that origin. The patterns of expansion help us understand the timeline of the universe, and by extension, hint at the conditions at its earliest stages. But as we consider what came before, we confront the limits of these observations. The Big Bang does not describe a conventional explosion in space. It describes the creation of space and time itself. Asking what came before is not like asking what happened before a sunrise or a historical event. Time itself begins with the Big Bang. Yet, physicists are not content to stop at this boundary. Using the principles of quantum mechanics, they attempt to extend our understanding beyond the classical singularity. Quantum cosmology seeks to describe the universe in terms of probabilities, waves, and fluctuating fields, rather than fixed points and lines. In this framework, the early universe is not a single moment of infinite density, but a region where space and time emerge from a quantum state that may not have classical analogues. One of the fundamental ideas is that of quantum fluctuations. Even in what we think of as empty space, tiny fluctuations in energy appear and disappear constantly. These fluctuations are a natural consequence of the uncertainty principle, which states that certain properties of particles, like their position and energy, cannot both be known precisely. In the earliest universe, these fluctuations would have been extreme, occurring in the very fabric of space and time. They could have seeded the irregularities that later grew into galaxies, stars, and planets. By imagining the universe at these smallest scales, we begin to glimpse how space and time themselves could have emerged from a quantum fog, a place where classical concepts of before and after are meaningless. The slow unfolding of the universe can be imagined as a transition from a state dominated by quantum effects to one in which space and time behave as we experience them. In this picture, the Big Bang is not a singular starting point in the usual sense, but a moment when the universe becomes classical and the familiar flow of time begins. Before that, the universe may have existed in a timeless quantum state. This does not mean there was nothing in a simple sense. Rather, there was a state that obeyed quantum laws without the usual structure of space or time. It is a subtle distinction, but one that allows scientists to speak meaningfully about before the Big Bang, even when conventional time did not exist. To explore this realm, physicists use mathematical models rather than direct observation. One influential approach is the Hartley-Hawking proposal, which suggests that the universe could have a no-boundary condition. In this model, time behaves more like a spatial dimension near the origin, so that the universe is finite but without an edge or singular starting point. It is like imagining the surface of a sphere. There is a beginning in some sense, but no sharp edge, no boundary where something suddenly appears. This idea allows scientists to describe the earliest universe in a way that avoids the infinities of classical singularities. It provides a bridge between quantum states and the expanding universe we observe today. These concepts may seem abstract, but they have consequences that can be tested. Tiny differences in the cosmic microwave background, patterns in the distribution of galaxies, and the search for primordial gravitational waves all carry information about the earliest quantum states. Every new measurement provides another piece of the puzzle, allowing scientists to refine their models of the universe before the Big Bang. Step by step, our understanding grows, revealing that the boundary between the known and the unknown is not an abrupt wall, but a subtle and intricate landscape, waiting to be explored with observation, mathematics, and imagination grounded in science. We are beginning to see that the question of what happened before the Big Bang is not unanswerable. It requires thinking beyond the usual flow of time, accepting that the universe may emerge from a state that is not bound by space and time, and using quantum theory to describe its earliest moments. The journey is slow and careful because every assumption must be consistent with the universe we see today. As we lie quietly and follow this story, we sense the enormity of the cosmos and the delicate precision of the laws that govern it. We understand that the beginning of everything is not a simple event, but a complex, fascinating process that stretches the limits of human understanding. The universe, as revealed by light, matter, and gravity, carries whispers of its own birth. In studying these whispers, we find patterns that hint at a pre-Big Bang state, a time when the ordinary rules of reality were suspended. It is a state that challenges our intuition, yet it is accessible to our minds through mathematics and careful observation. By examining the light from distant galaxies, by measuring the faint echoes of the cosmic microwave background, by listening for the ripples of gravitational waves, scientists are building a story that extends beyond the beginning, that allows us to imagine a world before space and time as we know them. Each discovery brings us closer to understanding the universe's ultimate origins, without resorting to fantasy or speculation, guided entirely by facts, evidence, and careful reasoning. The universe we see today is vast, stretching in all directions, filled with countless galaxies, stars, and planets. When scientists first looked carefully at the light coming from space, they discovered something remarkable. Everywhere they looked, there was a faint, uniform glow, a light that filled the universe like a quiet, invisible fog. This light is called the cosmic microwave background, or CMB. It is not like ordinary light that we see with our eyes. It is much older, a remnant from the early universe, a signal from the time when the cosmos was very young. About 380,000 years after the universe began, the cosmos had cooled enough for electrons and protons to combine into neutral atoms. Before this moment, the universe was a hot, dense plasma, opaque to light. Once atoms formed, light could travel freely, and this ancient light has been journeying through space ever since. By studying the CMB, scientists can see tiny patterns in temperature and density, small variations that eventually grew into the stars and galaxies we observe today. Every dot in the CMB map is a clue, telling a story of how the universe expanded, cooled, and shaped itself in its earliest stages. The discovery of the CMB was a turning point. Scientists had predicted that if the universe began in a hot, dense state, there should be leftover radiation from that early time. In 1965, Arno Penzias and Robert Wilson detected this radiation almost by accident. They found a constant background noise in their radio antenna, a noise that came from every direction in the sky. At first, it seemed like interference, but careful measurements confirmed that it was real and uniform. This faint glow confirmed that the universe had once been very hot and dense. The CMB is a snapshot, a photograph of the cosmos when it was a tiny fraction of its current size, providing a window into a time we could never otherwise see. Its uniformity and the subtle variations within it guide our understanding of the universe's early evolution. Another key piece of evidence comes from observing the motion of galaxies. Edwin Hubble, in the 1920s, found that galaxies are not stationary. Instead, almost all of them are moving away from us, and the farther a galaxy is, the faster it recedes. This motion is not just a simple movement through space, it is space itself expanding. Imagine the universe as a balloon with dots on its surface. As the balloon inflates, the dots move farther apart. This expansion means that, if we could reverse it, all galaxies would come closer together, tracing back to a much smaller, hotter, denser state. Hubble's observation provides a clear, measurable sign that the universe is growing, stretching the fabric of space over billions of years. It allows scientists to calculate the rate of expansion, called the Hubble constant, and to estimate the age of the universe. By combining this with other data, we learn not only how old the cosmos is, but also how it has changed from its earliest moments to the present day. The timeline of the universe begins with the Planck epoch, a time so early that our current understanding of physics cannot fully describe it. During this epoch, which lasted only a fraction of a second after the supposed singularity, the four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may have been unified into one. Space and time themselves were dominated by quantum effects, fluctuating and shifting in ways we can only attempt to describe mathematically. The Planck epoch is followed by the grand unification epoch, where gravity separated from the other forces and the universe continued to expand and cool. During this time, tiny quantum fluctuations set the stage for the large-scale structures we see today. These small differences in density would later grow, pulled by gravity, into the webs of galaxies and clusters that fill the universe. Next comes the inflationary epoch, a period of extremely rapid expansion that stretched the universe at a pace far beyond the speed of light. This inflation smoothed out irregularities, making the cosmos appear uniform on large scales, while preserving the tiny variations that would later form galaxies. After inflation, the universe entered the radiation-dominated era. It was filled with high-energy particles and photons colliding constantly in a dense, hot plasma. This chaotic sea of energy was opaque to light, so the universe was dark, even though it was full of light-producing particles. As the universe expanded, it cooled, and the particles gradually slowed down, eventually combining to form simple atoms. When the universe was about 380,000 years old, photons could travel freely, and the cosmic microwave background was released. This marks the point known as recombination, when the universe became transparent for the first time, allowing light to stream across space, carrying the story of the early cosmos. The CMB gives us a direct look at these processes. By measuring its temperature and the small ripples in its density, scientists can calculate the distribution of matter and energy in the young universe. These measurements tell us how fast the universe expanded, how much ordinary matter and dark matter exist, and how radiation influenced the formation of structure. The light has traveled for more than 13 billion years, cooling as it goes, until it reaches our instruments as faint microwaves. Its uniformity supports the idea of the Big Bang, while the tiny variations confirm the predictions of inflation. Each new observation adds precision, sharpening our understanding of the universe's first moments and the rules that governed its growth. Redshift measurements complement the CMB by tracing the expansion over time. Light from distant galaxies stretches as the universe grows, moving toward longer, redder wavelengths. By analyzing this redshift, astronomers can determine how fast objects move away and thus map the expansion history. Observing galaxies at different distances allows scientists to see the universe at different ages, creating a kind of cosmic time machine. Distant galaxies show conditions only a few 100 million years after the Big Bang, while nearby galaxies reflect the universe as it is today. These observations confirm the consistent expansion of space and reveal subtle changes over time, such as the effects of dark energy, which accelerates the expansion in the modern era. Together, The cosmic microwave background and the redshift of galaxies create a coherent picture. The universe began in a hot, dense state, expanded rapidly, cooled over time, and formed the structures we observe today. From the Planck epoch to recombination, every stage of the early universe is traced by these signals, allowing scientists to reconstruct the history of everything. Even though we cannot see the very first instant, the evidence from light and motion builds a bridge to that moment. It shows a universe that grew from simple beginnings to extraordinary complexity, governed by predictable laws, yet full of surprises waiting to be understood. In this way, the Big Bang Theory is not just an idea. It is a story written in the sky. Every galaxy, every photon, every faint ripple in the cosmic microwave background contributes to a record of what happened long ago. Scientists continue to measure, refine, and test this story, seeking ever more subtle clues about the earliest times. Observations of the oldest light, combined with the motion of galaxies and the study of large-scale structure, guide our understanding of the cosmos, bringing the distant past closer to our view. In lying here, quietly, listening to this story, one can imagine tracing the history of the universe backward, through cooling, expansion, and radiation, toward a time when the cosmos was small, hot, and dense, and the stage was set for everything that would come after. The universe, in its earliest moments, was unlike anything we see around us today. It was not filled with stars or galaxies, but with energy and potential, a space that was at once tiny and full of possibility. To understand this period, scientists use the rules of quantum mechanics, the branch of physics that governs the smallest scales of matter and energy. Quantum mechanics behaves differently from the classical world we experience. Particles can exist in multiple states at once, and energy can appear and disappear in ways that seem strange. In the early universe, these rules applied not just to particles, but to space and time themselves. The fabric of reality was not smooth or fixed. Instead, it was a dynamic and fluctuating stage, where even the concept of a definite location or precise moment in time is blurred. At this stage, space-time was influenced by quantum fluctuations, tiny random variations in energy that occur naturally. Even in what we think of as empty space, energy never truly disappears. Quantum mechanics allows it to rise and fall, to flicker in and out of existence. In the early universe, the density of energy was immense, and these fluctuations were magnified. Small differences in energy and matter created irregularities in the universe's structure. These minute variations would later grow into the large-scale patterns of galaxies, clusters, and cosmic voids. The irregularities left behind by these fluctuations can still be observed in the cosmic microwave background, showing faint differences in temperature and density. In this way, the smallest quantum effects played a decisive role in shaping the vast universe we see today. One way to think about this is to consider the uncertainty principle proposed by Werner Heisenberg. It states that we cannot know certain pairs of properties with perfect accuracy at the same time. For example, we cannot measure both the exact position and the exact speed of a particle. In the early universe, this principle applied not only to matter, but to energy and time. There is a limit to how precisely the energy of a system can be known over a very short period of time. When the universe was tiny and extremely energetic, these limits allowed for the spontaneous creation of energy fluctuations. These fluctuations provided the seeds for all future structure. Every galaxy, every star, every planet eventually formed from these tiny early differences. Without quantum mechanics, the universe would have been uniform and featureless, lacking the complexity we observe today. These quantum effects extend to space and time themselves. In the earliest moments, space may not have been smooth and continuous. Instead, it might have been granular, with tiny regions expanding and contracting in unpredictable ways. Time, too, may have been uncertain, not flowing evenly as we experience it now. This quantum nature of the early cosmos challenges our usual understanding of cause and effect. Events were governed by probabilities rather than certainties. Scientists use mathematical models called quantum fields to describe this period, allowing them to calculate the likelihood of different outcomes and to predict the patterns we can observe in the universe today. The results of these calculations match observations of the cosmic microwave background and the distribution of galaxies, confirming that quantum fluctuations left an imprint on the large-scale universe. Even though quantum effects dominate at the smallest scales, they have consequences for the universe as a whole. Tiny variations in energy density become magnified as the universe expands. Areas with slightly higher density attract more matter, pulling in surrounding material through gravity. Over time, this process leads to the formation of stars, galaxies, and clusters, while less dense regions become the vast voids that separate them. The simple, random flickers of energy in the first fraction of a second determine the complex structure of the universe billions of years later. Quantum cosmology, therefore, shows that the cosmos is deeply connected, from the smallest fluctuations to the largest formations. The relationship between energy and time in quantum mechanics also provides insight into the early universe's birth. Very brief moments allowed for large changes in energy, meaning that extreme conditions could exist for tiny fractions of a second. These brief spikes of energy could have caused rapid expansion, influenced the behavior of fundamental forces, and shaped the way space and time emerged. In other words, the earliest universe was a place where the rules of energy and time were flexible in ways that would be impossible under normal conditions. This flexibility allowed the universe to grow from a quantum state into the classical universe we recognize today, governed by predictable laws, but still carrying the traces of its uncertain beginning. Quantum cosmology also raises questions about what it means to have a beginning. In classical physics, the universe starts at a singular point, but quantum mechanics replaces the singularity with a probabilistic state. There is no exact location or instant where everything begins. Instead, there is a range of possible histories, each with its own probability. Some of these histories lead to the universe we see, while others may not. By calculating these probabilities, scientists can explore the most likely scenarios for the origin of space, time, and matter. This approach allows them to talk about the very earliest moments in a meaningful way, even when time itself is not fully defined. Observations provide indirect confirmation of these ideas. Patterns in the cosmic microwave background match the predictions of quantum fluctuations. Tiny temperature differences align with the scales expected from the uncertainty principle applied to the early universe. Large surveys of galaxies and clusters show structures that grew from initial variations in density consistent with quantum seeds. Every new piece of data strengthens the link between quantum mechanics and cosmology, showing that the same laws governing atoms and particles also shaped the entire cosmos. The early universe, though small and chaotic, was not random without reason. It followed the deep rules of quantum physics, leaving a traceable pattern that guides the formation of everything that followed. As the universe expanded, these quantum effects became less dominant, giving way to classical physics. Gravity, electromagnetism, and nuclear forces began to guide the motion of matter and energy in ways that are familiar today. But the imprint of quantum fluctuations remained, embedded in the large-scale structure of space. Each galaxy and star is a descendant of the tiny random variations that occurred in the first moments. Quantum cosmology teaches us that the universe is not just vast in size, but in its connections between scales. The smallest and largest phenomena are linked through a common set of rules that governed the birth of all that exists. In lying quietly and following this story, we can imagine the universe as it might have been in its first seconds. A place of uncertainty, flickering energy, and probabilistic outcomes, where space and time were not fixed, and where the seeds of all cosmic structure were sown. The laws of quantum mechanics shaped the early universe in ways both subtle and profound. Even though these effects are invisible to our eyes, they left a permanent imprint, a quiet trace that can be read by careful observation and measurement. Through quantum cosmology, scientists are able to connect the uncertain, chaotic beginning to the ordered universe we inhabit today, showing that even the smallest fluctuations in the earliest moments are crucial to the story of everything. After the first fractions of a second, the universe experienced a remarkable event called cosmic inflation. This was a period when space itself expanded at an incredible speed, faster than the speed of light. It was not that objects moved through space faster than light, but that space itself stretched, growing enormously in a tiny fraction of a second. Imagine a small balloon inflating almost instantly to a size larger than anything we can imagine. This expansion smoothed out the universe and set the stage for the structures that would later form. Inflation explains why the universe looks so uniform on large scales. In every direction we look, the cosmos appears similar, even though those regions could never have communicated with each other in ordinary time before inflation. This uniformity is one of the key pieces of evidence that inflation occurred. Observations of the cosmic microwave background confirm this story. The CMB is remarkably smooth, with only tiny variations in temperature. These tiny ripples are the remnants of quantum fluctuations that were stretched across the universe during inflation. Without inflation, these fluctuations would be far smaller, and the universe might appear irregular or clumpy on large scales. The patterns we see in the CMB match the predictions of inflationary theory, showing a nearly uniform background with subtle, organized differences. These differences later provided the seeds for galaxies and clusters of galaxies. By studying the CMB in detail, scientists can measure the scale of inflation and understand how it shaped the cosmos. Every observation supports the idea that a brief period of extreme expansion left a lasting mark on the universe. Inflation also solves puzzles that puzzled scientists for decades. One of these is called the horizon problem. In simple terms, different regions of the universe are so far apart that light or any signal could never have traveled between them since the beginning of time. Yet the universe looks nearly the same in every direction. Inflation explains this by stretching a small, already uniform region across the vast expanse of space. Before inflation, the universe was small enough that everything could interact and come to the same temperature. Then, inflation stretched it, carrying that uniformity over unimaginable distances. The horizon problem is resolved because what we see today was once part of a tiny connected patch of the early universe. Another puzzle is the flatness problem. Observations show that the universe is very close to flat, meaning that its geometry follows the rules of Euclidean space on large scales. Small deviations from flatness in the early universe would have grown over time, leading to a highly curved or unstable cosmos. Inflation explains this by smoothing out curvature. As space expanded exponentially, any initial curvature became negligible, leaving the universe looking flat on scales we can observe. The flatness we measure today is therefore a natural consequence of inflation, rather than a coincidence. It shows that the universe did not require precise tuning to achieve the geometry we see. The mechanism of inflation involves a type of energy field that dominated the early universe. This field, sometimes called the inflaton, caused space to stretch rapidly. As the field slowly lost energy, inflation ended, and the universe entered a more stable expansion phase, dominated first by radiation and later by matter. During inflation, the tiny quantum fluctuations in this field were stretched to cosmic scales. These stretched fluctuations became the seeds of large-scale structures, linking the smallest scales of quantum uncertainty to the vastness of galaxies and clusters. In this way, inflation connects the microscopic world of quantum mechanics with the macroscopic universe we observe today. Inflation also sets initial conditions for later evolution. The rate of expansion determines how the universe cools, how particles form, and how energy and matter interact. Small differences in density, amplified by inflation, explain the cosmic web, the network of filaments and voids that fills space. Without inflation, the universe might have been too irregular or too uneven to form galaxies and stars in the way we see. Inflation provides a natural explanation for the smooth, uniform background and the small, structured deviations that lead to complexity. It is a theory that explains not just one feature of the universe, but many, showing how a brief period of rapid expansion shaped the cosmos in multiple ways. Evidence for inflation also comes from the study of gravitational waves. These are ripples in space-time caused by extreme events. In the early universe, inflation may have produced very faint gravitational waves, stretching space itself. Scientists are searching for these signals in the polarization of the cosmic microwave background. If detected, they would provide a direct confirmation of inflation and the extreme conditions of the first moments. Every experiment and observation, from satellites measuring the CMB to ground-based detectors, adds pieces to this puzzle, allowing scientists to test theories of inflation and refine the story of the early universe. Inflation is not just a theoretical idea. It explains why the universe is so uniform, why its geometry is flat, and why structures exist at the scales we see. It connects quantum fluctuations with cosmic structures, showing how the smallest possible effects can shape the largest features of reality. The theory also predicts patterns that are observable, giving scientists measurable ways to confirm or challenge its ideas. By studying these patterns, researchers gain insight into the earliest moments, linking the invisible and incomprehensibly fast expansion of inflation to the observable universe today. Lying quietly, one can imagine the universe inflating from a tiny, dense region into an immense, smooth expanse. Quantum ripples are stretched into faint waves across space, providing the seeds of all cosmic structures. The universe, once uncertain and chaotic at tiny scales, becomes ordered and organized as inflation ends. Space is still expanding, but the rules governing matter and energy now follow familiar laws. Inflation is the bridge between the mysterious quantum beginnings and the predictable classical universe. It shows that the universe's vastness and uniformity are not accidents, but natural outcomes of processes that occurred in the first moments after the beginning. Even though the details of inflation involve complex physics, the simple idea is clear. A brief, rapid stretching of space smoothed the universe, set its geometry, and left behind the fluctuations that would grow into galaxies. Observations of the cosmic microwave background, the structure of the cosmos, and searches for gravitational waves provide supporting evidence. Inflation connects the early quantum-dominated universe to the classical cosmos, linking small fluctuations to enormous structures. As we lie quietly, listening to this story, we can imagine the universe growing almost instantly from a tiny patch into the vast expanse we now inhabit. Every galaxy, every star, every faint ripple in the cosmic microwave background carries the signature of that moment of rapid expansion, reminding us of the universe's extraordinary and carefully balanced beginnings. Even as scientists understand the universe after the Big Bang, questions about what came before remain. Several ideas have been proposed, each trying to explain how the universe could exist before space and time as we know them. One class of ideas is called ekpyrotic or cyclic models. In these models, the universe is not a one-time event. Instead, it goes through repeated cycles of contraction and expansion. A previous universe could have shrunk, compressed to a very small, dense state, and then expanded again to form the universe we see today. This process could repeat over vast periods, with each cycle creating conditions similar to a new Big Bang. The cyclic model offers a way to imagine a before without requiring a single absolute beginning. It proposes that the universe has a rhythm, a slow, continuous heartbeat, where each cycle leaves traces that influence the next. Another approach is based on quantum gravity, which tries to combine the laws of quantum mechanics with Einstein's theory of general relativity. One example is loop quantum cosmology. In this model, space and time are made up of tiny discrete units, like grains in a lattice. Near what would be a classical singularity, these discrete units prevent infinite density. Instead of a true singular beginning, the universe experiences a bounce. The contraction of a previous universe reaches a minimum size, then bounces back, expanding into the universe we observe. Loop quantum cosmology avoids the problem of infinite density, providing a continuous evolution of space and time. It shows that the Big Bang might not be the absolute beginning, but a transitional phase from a previous cosmic state. This model also produces testable predictions, such as patterns in the cosmic microwave background, which could reveal the effects of the previous contraction. String cosmology offers a different perspective, using ideas from string theory. In string theory, the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. These strings exist in multiple dimensions, far beyond the three of space and one of time that we experience. One scenario involves brains, large multidimensional surfaces which can collide with each other. A collision between two brains could produce a universe like ours, with energy and matter spreading outward. This process could be interpreted as a type of Big Bang. In string cosmology, the universe we observe may be one of many possible outcomes of brain interactions. These models open the possibility that the cosmos existed in some form before the Big Bang, in a higher dimensional space that is usually invisible to us. Like other pre-Big Bang ideas, string cosmology is constrained by observations, such as the uniformity of the cosmic microwave background, which limits how extreme or violent these collisions could have been. Each of these models faces constraints from both theory and observation. Any successful scenario must match the facts we see today. The cosmic microwave background provides detailed information about the early universe's temperature and density variations. Observations of galaxy distributions, gravitational waves, and the overall expansion rate set additional limits. For example, cyclic models must allow enough time and energy to produce the smooth, uniform conditions observed in the CMB. Loop quantum cosmology must ensure that a bouncing universe leaves patterns consistent with current measurements. String cosmology must produce the right amount of energy and avoid leaving signatures that contradict the CMB's near uniformity. By comparing predictions with observations, scientists can rule out certain variations and refine the models that remain plausible. These models also highlight the interplay between mathematics and observation. They provide frameworks to describe phenomena far beyond direct human experience. Even if we cannot see a previous universe or a higher dimension directly, the effects of such scenarios might leave subtle imprints. Tiny differences in the cosmic microwave background, the distribution of matter, or the polarization of light could reveal traces of a pre-Big Bang state. Each model makes specific predictions about these traces, and as measurements become more precise, some scenarios may gain support while others are constrained or discarded. This careful comparison ensures that the search for pre-Big Bang physics remains grounded in evidence. The ikperotic model emphasizes smooth, slow contraction before expansion. It predicts small differences in density that align with observed patterns in the CMB. Loop quantum cosmology predicts a bounce, replacing the singularity with a high-density phase that retains the memory of a previous universe. String cosmology predicts that brain collisions could generate fluctuations in energy and matter, which might appear as tiny anomalies in the cosmic microwave background. Each scenario provides a way to imagine before, in scientific terms, without appealing to speculation or fantasy. They are rooted in physics, constrained by observations, and formulated to make predictions that can, in principle, be tested. These pre-Big Bang models also challenge how we think about time and causality. In cyclic and loop models, time may extend infinitely into the past, with no absolute beginning. In brain collision models, time may be a derived property, emerging only after higher dimensional interactions. These concepts stretch our understanding of what it means for the universe to exist, showing that beginnings may not be simple points, but processes that unfold according to deep physical laws. They suggest that the universe is resilient and structured, capable of emerging from previous states or higher dimensional interactions. In each case, the observed universe is shaped by constraints and processes that preceded the Big Bang itself. In quiet reflection, it is remarkable that scientists can form coherent ideas about events beyond direct observation. Using mathematics, physics, and detailed measurements, researchers can construct possible histories of the cosmos that extend before the moment we call the Big Bang. Every new observation tests these ideas, sharpening our understanding. Even when the universe seems to begin in a singular hot state, these models remind us that nature may be more subtle. The pre-Big Bang world, whether it was a contracting universe, a quantum bounce, or a higher dimensional collision, is accessible to human thought through careful reasoning and evidence. It may forever remain hidden from direct view, but its influence is imprinted in the universe we see today. By exploring ekpyrotic cycles, quantum bounces, and brain collisions, scientists expand our imagination in a disciplined way. They show that before is not meaningless, even when time as we know it begins with the Big Bang. Observational tests keep these ideas grounded. Future measurements of the cosmic microwave background, gravitational waves, and the distribution of galaxies may provide clues to distinguish between these models. The search for pre-Big Bang physics is a slow, careful journey, requiring patience, precision, and a willingness to follow the evidence wherever it leads. It connects the tiniest quantum scales to the largest cosmic structures, illustrating the depth and richness of the universe's earliest history. In lying quietly, one can picture the universe as a sequence of possibilities, each emerging from laws that govern matter, energy, space, and time. Cycles may repeat, bounces may occur, brains may collide. The universe we inhabit is shaped by processes that extend far beyond the simple beginning of the Big Bang. Each idea is rooted in evidence, mathematics, and careful reasoning. Observations of the cosmic microwave background, galaxy formation, and large-scale structure provide guideposts, showing what is possible and what is unlikely. The universe, even in its earliest moments, is not chaotic without pattern. It follows principles that scientists can understand and explore. These models of the pre-Big Bang cosmos reveal a universe that is deep, interconnected, and shaped by processes that began long before the familiar flow of time. Thinking about what happened before the Big Bang can be difficult because the concept of before depends on time. In our daily lives, before means an earlier moment in a sequence. But if time itself began with the Big Bang, asking what came before is not the same as asking what happened yesterday. Time may not exist in the usual sense prior to the beginning of the universe. This idea challenges the way we normally think about cause and effect. Physicists and philosophers alike explore what it means for something to exist without time. They try to imagine a reality where events are not ordered by seconds or minutes, and where change happens differently, if at all. In this realm, before does not refer to an earlier tick of a clock, but to a state that allows time to emerge. Some theories suggest that time is not fundamental, but emergent. That is, time may arise from deeper processes, like a property that appears when certain conditions are met. In these models, the universe does not require a singular beginning in the ordinary sense. Instead, space and time could develop gradually from a quantum state. Before time emerges, the universe exists in a form that is fundamentally different from what we experience. It may be a state where relationships and possibilities exist, but without a measurable duration. This emergent perspective changes how we think about the origin of the cosmos. The Big Bang becomes a transition point, a moment when time starts to flow, rather than a sharp starting line of existence. Timeless quantum states offer a way to describe this pre-time universe. In quantum mechanics, systems can exist in superpositions, holding multiple possibilities at once. Applying this to the cosmos, the universe can be in a state that is not defined by conventional time. It is a probability landscape with many possible outcomes from which a universe with classical space and time can emerge. This approach allows scientists to model the earliest moments without requiring time itself to be present. It also connects with the idea of quantum fluctuations, where energy varies unpredictably. Even without time, these fluctuations provide structure and allow the universe to develop patterns that later become space and matter. The Hartley-Hawking no-boundary proposal is one of the most influential ideas in this domain. According to this model, the universe does not have a sharp starting point or singularity. Instead, it is finite but has no boundary, much like the surface of a sphere. A sphere has a shape, but it does not have an edge. Similarly, the universe could have a smooth, rounded geometry in a higher dimensional space, where time behaves like a spatial dimension near its origin. In this view, the universe simply is, without a boundary, and time emerges gradually as the universe grows. There is no need to ask what came before, because the concept of before does not apply in the same way. The beginning is more like the top of a sphere than the first tick of a clock. The no-boundary proposal has practical implications for understanding the early universe. It provides a framework for calculating probabilities of different cosmic histories. By using the laws of quantum mechanics and general relativity, scientists can estimate how likely it is for a universe like ours to emerge. This approach predicts a smooth beginning with low entropy, which naturally leads to the expansion we observe today. It also explains why the universe is uniform and nearly flat, without requiring extreme fine-tuning. The proposal turns the problem of a beginning into a question of geometry and probability, rather than a moment in time that needs a cause. It is a powerful tool for connecting timeless quantum states to the observable universe. Emergent space-time and the no-boundary idea both suggest that the universe did not need a classical past. The familiar flow of seconds, minutes, and hours is a feature that appears only after the universe expands and cools. Before that, there may have been a state where all possibilities existed at once, governed by probabilities and quantum laws. In this framework, the Big Bang is less an event in time than a phase transition, a shift from timeless quantum potential to classical space-time and energy. It allows scientists to think about origins in a meaningful way, while avoiding contradictions with known physics. Even though we cannot directly experience this pre-time reality, its consequences are observable in the structure of the universe and the patterns we see in the cosmic microwave background. This perspective also reshapes philosophical ideas about beginnings. If time emerges, then cause and effect may not apply in the usual way at the universe's origin. The universe could exist without a first cause, in a sense that is meaningful within the rules of quantum mechanics. Probabilities replace certainties, and the concept of before is replaced with a landscape of possible states. Each possibility could lead to a universe with slightly different properties, Yet only some of these histories result in the smooth, structured cosmos we inhabit. This approach bridges the gap between physics and questions of existence, providing a scientific framework for understanding origins without invoking metaphysics or speculation. Observations help constrain these ideas. Patterns in the cosmic microwave background and the distribution of matter and galaxies reflect the earliest stages of space-time. The near uniformity and small variations are consistent with a smooth beginning, as predicted by the no-boundary proposal. Measurements of the universe's expansion, combined with quantum cosmology models, provide additional checks. While we cannot see timeless states directly, we can infer their properties by looking at the universe today. These constraints allow scientists to evaluate theories, favoring those that produce results consistent with observation and discarding those that do not. The universe becomes a record, a reflection of what must have occurred, even when time was not yet defined. Imagining a timeless state challenges intuition. Without seconds or minutes, without change as we know it, the universe exists in a way that is hard to picture. Yet, mathematics allows scientists to describe these states, calculate probabilities, and predict outcomes. By thinking of time as emergent, researchers can model the transition from quantum potential to classical space-time. They can explore how the first structures arise, how expansion begins, and how conditions for inflation or the Big Bang itself emerge. This theoretical framework provides a coherent, scientifically grounded way to discuss origins without requiring time to exist prior to the beginning. In quiet reflection, one can picture the universe in this early phase, not moving forward or backward, not aging or changing in a normal sense, but existing as a whole set of possibilities. Space and time are latent, waiting to emerge from the underlying quantum reality. The smooth, almost featureless beginnings that lead to inflation and later structure are encoded in this timeless state. The universe unfolds gradually, guided by laws that operate without reference to ordinary time. Eventually, classical space and time emerge, forming the familiar cosmos that stretches from the Big Bang to the present. The flow of time, the ticking of moments, is a product of this transition, not a pre-existing condition. Through emergent space-time and the no-boundary proposal, scientists find ways to understand the universe before time itself. It is a state that defies everyday experience, yet it can be described, analyzed, and connected to observations. The cosmic microwave background, galaxy formation, and large-scale structure all carry traces of this phase. The story of the universe does not begin with a single point in time, but with the unfolding of quantum possibilities. Each moment, each structure, is a result of that emergence. By listening to this story quietly, one can sense the deep, subtle processes that bring time, space, and matter into existence, forming the stage on which the universe continues to evolve. As the universe approaches the earliest moments, the laws we normally use begin to fail. Einstein's theory of general relativity describes how gravity shapes space and time, and it works extremely well for stars, planets, and galaxies. However, near the singularity of the Big Bang, densities and energies become so extreme that general relativity can no longer provide accurate predictions. Space and time themselves reach conditions where the smooth, continuous fabric assumed by relativity breaks down. At these scales, quantum effects cannot be ignored. The very rules that govern the motion of planets or the bending of light are replaced by the strange probabilistic rules of quantum mechanics. Scientists refer to this as the breakdown of classical physics, and it signals the need for a theory that can combine gravity with quantum principles. To address this, researchers explore approaches collectively called quantum gravity. One approach is loop quantum gravity, which treats space itself as made up of tiny, discrete units. Instead of being smooth, space has a fine structure like a woven fabric. Near what would have been a singularity, these units prevent infinite densities, replacing the classical point of the Big Bang with a quantum phase. This model predicts a bounce, where a contracting universe transitions smoothly into an expanding one. Loop quantum gravity also provides a framework to describe early fluctuations and the emergence of classical space-time. By studying how quantum units interact, scientists can begin to understand what conditions existed at the earliest scales, where ordinary ideas of distance and time lose meaning. String theory offers a different perspective. In this view, the fundamental constituents of reality are not point-like particles, but tiny, vibrating strings. These strings can vibrate in different ways, producing the variety of particles and forces we observe. String theory naturally incorporates gravity along with other forces, offering a potential unifying framework. It also suggests the existence of extra dimensions beyond the familiar three of space and one of time. These dimensions may influence the behavior of the universe at very early times. In string cosmology, interactions between strings and higher dimensional objects called branes could shape the formation of the universe, providing mechanisms for the Big Bang and for features we see today. Both loop quantum gravity and string theory attempt to describe conditions where general relativity no longer applies, each offering distinct but complementary views of the earliest universe. The unification of gravity with quantum mechanics is not only a theoretical goal, but also a way to predict observable effects. Tiny fluctuations in the early universe, stretched by inflation, may carry signatures of quantum gravity. These could appear as specific patterns in the cosmic microwave background, or as subtle anomalies in the distribution of galaxies. Certain models predict faint gravitational waves, ripples in space-time, created in the earliest moments. Detecting these signals would provide direct evidence of the quantum structure of space and the processes that occurred near the origin. Scientists are developing increasingly sensitive instruments to look for these effects, aiming to connect theories of quantum gravity with measurable reality. Even though we cannot directly observe the singularity, indirect observations give clues. The cosmic microwave background preserves information about density fluctuations and temperature variations that were influenced by early physics. By carefully measuring these patterns, researchers can compare them with predictions from loop quantum gravity, string cosmology, and other models. The shape, scale, and distribution of fluctuations act like a fingerprint of the universe's earliest moments. Each observation constrains possible theories, allowing some scenarios to gain support while others are ruled out. In this way, the study of quantum gravity becomes tied to tangible evidence, bridging abstract theory and observable cosmos. Quantum gravity also raises new questions about the origin of matter and energy. In classical physics, energy and mass emerge after the Big Bang. In quantum models, the distinction between energy and space may be less clear. The universe could begin as a quantum state, where energy, matter, and space are intertwined. As the universe expands, these components separate, forming particles, radiation, and the structure we recognize. Loop quantum gravity envisions discrete steps in this emergence, while string theory describes vibrations and interactions in higher dimensions. Both approaches suggest that the universe's contents arise naturally from fundamental principles, without requiring arbitrary conditions or external causes. The search for observable signatures is ongoing. Scientists look for anomalies in the cosmic microwave background, gravitational waves, and patterns in the large-scale distribution of galaxies. Each of these may contain subtle hints of quantum gravity or pre-Big Bang physics. The earliest fluctuations could leave imprints in polarization, temperature gradients, or density distributions. Even tiny deviations from predicted patterns are important, as they might distinguish between competing theories. By comparing observation with theoretical predictions, researchers aim to find the first direct evidence of quantum gravity at work, shedding light on a period of the universe that is otherwise inaccessible. Loop quantum gravity and string theory also offer different implications for the evolution of the universe. In loop models, a previous contraction influences the current expansion, potentially leaving residual effects in the cosmic structure. String models suggest that extra dimensions or brane interactions could have shaped the initial energy distribution and influenced inflation. Both models provide a path to understanding why the universe is uniform, yet contains structured variations. These ideas connect the very small with the very large, showing that quantum processes can have lasting effects on cosmic scales. Every galaxy, every cluster, and every subtle pattern in radiation may trace back to these earliest dynamics. Even though many details remain speculative, the pursuit of quantum gravity reveals the deep unity of nature. Gravity, space, time, matter, and energy are not separate entities, but aspects of a single underlying framework. By understanding how these elements interact at the smallest scales, scientists hope to answer fundamental questions. Why does the universe exist? How did it emerge from an extreme quantum state? How did classical space-time and matter arise from the quantum foam of the earliest moments? These questions guide research in theoretical physics, astrophysics, and cosmology, connecting abstract mathematics with the observable universe. As we lie quietly, imagining the earliest universe, we can picture a realm where space is granular, time is emerging, and matter is just beginning to take form. Tiny fluctuations ripple across this quantum landscape, stretching under inflation and influencing the future structure of the cosmos. Gravity is no longer a smooth force, but a quantum phenomenon, interwoven with energy and matter. String vibrations and loops of space combine to produce the seeds of galaxies and stars. Even without directly seeing these processes, scientists trace their effects in the patterns left behind, revealing a universe that is both mysterious and comprehensible, shaped by principles that operate at the smallest scales, yet leave lasting marks on the largest scales. Quantum gravity and unifying theories remind us that the universe's beginning is not merely a singular point, but a complex phase governed by rules that differ from those of everyday life. It is a bridge from timeless quantum possibilities to the classical cosmos, linking what we can observe today with processes that occurred at scales far smaller than an atom. Observations and theory together guide our understanding, suggesting that the universe's structure, behavior, and very existence are rooted in quantum laws. By studying these laws, scientists illuminate the first moments and explore what may have preceded the familiar flow of time and space, revealing a cosmos far richer and more intricate than ordinary experience suggests. As scientists examine the early universe, some theories suggest that our cosmos may not be the only one. The idea of a multiverse arises naturally from quantum mechanics and inflationary cosmology. In this view, the universe we inhabit is just one of many, each emerging from separate quantum events or inflationary expansions. The multiverse concept provides a framework to consider realities beyond our observable cosmos, where different physical conditions, energies, or laws might exist. It expands our understanding of existence, suggesting that what we call the Big Bang may be one event in a vast, ongoing process that creates multiple universes, each with its own history. One way the multiverse could form is through bubble universes. During inflation, space expands extremely rapidly. Tiny fluctuations in energy can cause local regions to stop inflating while others continue. The regions that stop can form bubbles, each becoming a separate universe with its own space, time, and physical properties. The surrounding space may continue inflating, creating more bubbles over time. In this picture, the cosmos is like a foam of countless universes, each isolated and independent. Some may resemble our universe closely, while others may differ in fundamental constants or the types of particles they contain. The bubble universe model illustrates how many possible realities could emerge from the same underlying processes. Eternal inflation is closely linked to the multiverse. In this scenario, inflation never completely ends. While some regions stop inflating and form individual universes, other regions continue to expand, producing new bubbles indefinitely. The process goes on forever, creating an unending sequence of universes. Each new bubble is a potential universe, distinct from all others, and each follows its own physical evolution. Eternal inflation changes the way we think about the beginning. There may not be a single, unique Big Bang. Instead, the origin of our universe is just one of countless beginnings occurring within a larger, ever-expanding multiverse. It transforms the idea of a singular origin into a more distributed and ongoing process. The multiverse perspective affects how we think about time and causality. In a multiverse, the question of what came before the Big Bang becomes more complex. Our universe may have a starting point, but that point exists within a larger multiversal landscape. There may be no absolute beginning for the multiverse as a whole. Time within each bubble may begin when inflation ends locally, but the larger inflating space may exist without a clear beginning. This approach connects to earlier ideas about emergent time and timeless quantum states, extending them to a broader scale. Before, the Big Bang of our universe may be meaningless in a global sense, because the multiverse does not follow the same time rules that we experience. Quantum mechanics plays a role in multiverse formation as well. Tiny, random fluctuations in energy during inflation can influence which regions stop expanding and form bubble universes. These fluctuations are unpredictable, but follow statistical laws. Each bubble's properties are determined by the outcome of these quantum events. In this way, the universe we inhabit is a natural consequence of probability within a larger multiverse. Other universes may have different fluctuations, leading to different physical properties. The multiverse concept shows how the smallest quantum processes can produce enormous consequences, creating entire universes with distinct characteristics. Observationally, evidence for a multiverse is challenging to obtain. Since other universes are likely separated from ours by vast inflating space, direct detection may be impossible. However, subtle signs could exist. Collisions between bubble universes might leave traces in the cosmic microwave background or other cosmic structures. Patterns in radiation, unusual distributions of galaxies, or unexpected gravitational signals could hint at interactions with other universes. While direct proof is difficult, the multiverse remains a mathematically and physically consistent possibility, supported by our understanding of quantum mechanics and inflation. It is a framework that extends existing cosmology into a much larger context. The multiverse also offers explanations for some fine-tuned features of our universe. Certain constants, like the strength of gravity or the properties of matter, appear finely balanced to allow stars, planets, and life to exist. In a multiverse, these constants may vary from one bubble to another. We find ourselves in a universe capable of supporting complexity simply because only such universes allow observers to exist. This idea, called the anthropic principle, provides a different way to interpret the conditions we observe. Rather than assuming our universe is uniquely designed or improbable, the multiverse suggests that many universes exist, but we experience the one suitable for life. It shifts the perspective from necessity to probability. Considering the multiverse reshapes the narrative of cosmic beginnings. The Big Bang becomes a local event, one of many possible expansions occurring within a larger, ongoing process. Each bubble universe carries the imprint of its quantum origin and the inflationary mechanisms that shaped it. While our universe has a history, structure, and observable evolution, it is part of a vast ensemble of universes. This broader perspective highlights the richness and complexity of existence, showing that our familiar cosmos may be just a small part of an unimaginably vast, multiversal reality. Lying quietly, one can imagine the universe as a single bubble floating in a vast, inflating space. Other bubbles form in every direction, each with its own unfolding history. Some may contain matter and energy similar to ours. Others may have completely different physics. The multiverse connects with earlier discussions of quantum fluctuations, inflation, and pre-Big Bang scenarios, extending them into a framework that encompasses infinite possibilities. It shows that our universe's beginning, while unique to us, may be part of a larger, ongoing process that has no absolute starting point and no fixed boundary. The story of existence becomes broader, more intricate, and deeply connected to the laws of physics that govern even the earliest moments of space-time. Even without direct evidence, the multiverse encourages scientists to think beyond the observable horizon. It suggests that cosmic inflation and quantum mechanics produce a rich and varied landscape of possibilities. While our universe is the one we inhabit and can observe, it is not the only one that could emerge from the same physical laws. The processes that shaped our cosmos could repeat endlessly, creating countless universes, each with its own Big Bang-like beginning. The multiverse provides a context for understanding why our universe exists as it does, why it is uniform yet structured, and how the earliest quantum and inflationary events connect to the vast cosmic tapestry beyond our sight. It invites us to expand our understanding of before the Big Bang and to appreciate the depth and complexity of existence itself. As our understanding of the early universe deepens, scientists rely on observations and experiments to test their ideas. The cosmic microwave background, the faint glow left from the earliest hot phase, is one of the most important tools. By studying the polarization of this light, researchers can detect tiny patterns imprinted by processes like inflation. These patterns provide clues about the structure of space-time in the first fractions of a second. Subtle twists and alignments in the polarization may reveal the presence of primordial gravitational waves, ripples in space-time produced during extreme events near the origin. Measuring these faint signals requires sensitive instruments, but they can carry direct evidence of the universe's earliest physics, connecting theory with observation. Large-scale structure surveys complement the study of the cosmic microwave background. By mapping the distribution of galaxies and galaxy clusters across billions of light-years, scientists can reconstruct how matter evolved from tiny fluctuations in the early universe. The positions, densities, and shapes of these cosmic structures reflect the influence of quantum fluctuations and inflationary expansion. Each survey adds detail, revealing the way gravity, energy, and matter combined to form the web-like patterns seen today. By comparing observations with theoretical predictions, researchers can test models of the early universe, from inflation to quantum gravity. The large-scale universe becomes a record of processes that occurred long before stars and galaxies existed. Particle accelerators also play a role in exploring early universe physics. Machines like the Large Hadron Collider recreate conditions similar to those in the first microseconds after the Big Bang. By colliding particles at high energies, scientists probe fundamental forces, search for new particles, and study interactions that shaped the universe's evolution. Experiments can reveal properties of the Higgs field, investigate matter-antimatter asymmetry, and explore the behavior of quarks and leptons at extreme energies. While these accelerators cannot reproduce the universe itself, they allow detailed study of the physics that governed the earliest stages, providing a bridge between laboratory experiments and cosmic history. Despite these advances, testing pre-Big Bang scenarios directly remains extremely challenging. Concepts like cyclic universes, quantum bounces, and multiverse formations often involve conditions beyond observational reach. Many of these ideas describe states that cannot be accessed by light or matter, existing beyond the observable horizon or in higher dimensions. Scientists rely on indirect evidence, such as patterns in the cosmic microwave background, gravitational waves, or statistical properties of large-scale structures. Even slight anomalies can suggest the influence of earlier states or unknown physics, but confirming specific models is difficult. The frontier of early universe research lies in extracting the maximum information from subtle signals, interpreting them carefully, and refining theories in light of what is measurable. Gravitational wave astronomy is opening new windows into the earliest moments. These waves carry information about disturbances in space-time from periods otherwise invisible. Primordial gravitational waves, if detected, would provide direct evidence of processes occurring near the start of inflation or even earlier. Instruments such as space-based detectors and ground interferometers aim to measure these faint ripples. Each detection could reveal features of quantum fluctuations, inflation, or the energy content of the very early universe. gravitational waves complement electromagnetic observations, offering a fundamentally different way to probe cosmic origins, independent of light or matter. Observational efforts are complemented by theoretical modeling. Researchers simulate the evolution of the universe under various assumptions, from inflationary dynamics to quantum gravity effects. These simulations predict what patterns should appear in the cosmic microwave background, galaxy distributions, and gravitational wave signals. By comparing simulations with observations, scientists can narrow the range of plausible scenarios. This iterative process, where theory guides observations and observations refine theory, is essential for studying phenomena that are otherwise beyond direct reach. Even if we cannot see a pre-Big Bang state, its consequences may be inferred through careful analysis of the structures and signals we can measure. Challenges remain in connecting high-energy particle physics with cosmology. Conditions in accelerators differ from the early universe in scale, duration, and context. Nevertheless, studying particle interactions at extreme energies provides essential insight into symmetry breaking, field behavior, and fundamental forces. This information feeds back into cosmological models, helping scientists predict the evolution of matter and energy in the first fractions of a second. The combination of astrophysical observations and laboratory experiments allows a more complete picture, linking the very small to the very large, and offering a pathway to test ideas about the origins and early evolution of the cosmos. Other observational frontiers include the study of cosmic rays, neutrinos, and dark matter. High-energy cosmic particles may carry information about processes that occurred in the early universe. Neutrinos, which interact very weakly with matter, can escape from dense regions and provide indirect glimpses of high-energy events. Observations of dark matter, although challenging, constrain models of particle formation and the distribution of mass in the universe. Together, these lines of research create a network of evidence that informs theories of early cosmology, even in the absence of direct access to pre-Big Bang states. Each measurement, however subtle, helps piece together the complex history of the universe. In quiet reflection, one can imagine scientists carefully measuring the faint glow of the cosmic microwave background, listening for the gentle ripples of gravitational waves, and analyzing data from particle collisions. Each effort brings us closer to understanding the universe's first moments and the conditions that led to the Big Bang. Observations and experiments provide a window into times that are otherwise inaccessible, revealing how fundamental forces, quantum fluctuations, and inflation shaped the cosmos. They also highlight the limits of our current knowledge, showing where imagination, careful theory, and technological innovation must meet to uncover the story of beginnings. Even with these tools, scientists recognize the profound difficulty of studying the pre-Big Bang universe. Many possibilities remain, from bounces and cyclic models to the multiverse. Observations can constrain these ideas, but some aspects may always remain beyond direct verification. The approach is therefore cautious, evidence-driven, and iterative. By combining precise measurements, theoretical modeling, and creative reasoning, researchers continue to expand the boundaries of what is known. Each new experiment, each refined observation, contributes to a deeper understanding of the universe's origin and the processes that led to the cosmos we observe today. The frontier of early universe science is one of patient exploration. It requires careful attention to tiny signals, subtle patterns, and rare events. By mapping the cosmos, probing fundamental particles, and seeking faint gravitational waves, scientists explore the hidden chapters of cosmic history. Every photon from the cosmic microwave background, every ripple in space-time, every high-energy particle in a detector carries information about the first moments. Even when direct observation is impossible, careful measurement and analysis allow inferences about the pre-Big Bang universe, providing a bridge from theory to evidence and bringing humanity closer to understanding the deepest origins of reality. As we look back over the story of the universe, it becomes clear that science has uncovered remarkable truths about its origin. From the Big Bang to the formation of galaxies, stars, and planets, we have traced the evolution of the cosmos with increasing precision. Observations of the cosmic microwave background reveal the earliest fluctuations in energy and matter, showing how a nearly uniform universe gradually developed structures. The expansion of space, measured through the redshift of distant galaxies, confirms that the universe is growing and changing. These discoveries provide a solid foundation for understanding the sequence of events from fractions of a second after the Big Bang to the present day. They are rooted in careful measurement, logical reasoning, and the consistent application of physical laws. Beyond these well-established facts, scientists have proposed models to explain what may have occurred even earlier in realms that challenge ordinary experience. Quantum cosmology suggests that the first moments involved fluctuations at the smallest scales, where space and time are governed by probability rather than certainty. Inflationary theory describes an extraordinary expansion that smoothed the universe and seeded the formation of galaxies. Pre-Big Bang scenarios, including cyclic models, loop quantum cosmology, and string theory brain interactions, offer glimpses of possibilities that extend our understanding beyond classical time. Each model is grounded in mathematics and constrained by observation, yet each stretches the imagination and challenges intuition. They illustrate how the universe's earliest history may be richer and more complex than what is directly observable. The multiverse hypothesis expands this view even further. In this framework, our universe is one of many, each emerging from quantum fluctuations or inflationary events. The concept of bubble universes and eternal inflation suggests that new universes may form continuously with different properties, laws, and histories. Within this picture, our Big Bang is a local event embedded in a broader cosmic landscape. While direct evidence for other universes remains elusive, the possibility invites us to think about the cosmos in terms that go beyond a single observable reality. It encourages a sense of humility, reminding us that what we see may represent only a fraction of a larger structure that is largely beyond reach. Despite these advances, fundamental questions remain. What, if anything, preceded the emergence of space and time? How did quantum laws give rise to the familiar flow of events? Is there a true beginning, or is time an emergent property arising from deeper structures? The Hartley-Hawking no-boundary proposal, emergent space-time theories, and quantum gravity models all provide frameworks for approaching these questions, but uncertainty remains. Observation can only reach so far, and some aspects of pre-Big Bang physics may remain forever inaccessible. Yet, even within these limits, human reasoning and measurement allow us to build coherent, evidence-based models that connect the smallest scales of reality with the largest structures of the cosmos. Reflecting on the human perspective, it is remarkable that we can consider events occurring at incomprehensible energies and densities, long before galaxies, stars, or planets existed. We can trace the consequences of tiny quantum fluctuations to the formation of the universe we inhabit. From delicate measurements of the cosmic microwave background to theoretical explorations of higher dimensions, we are able to reconstruct a narrative of beginnings that stretches across billions of years. Even the possibility of multiple universes, while speculative, is consistent with known physics and provides a framework for thinking about why our universe exhibits the properties it does. These insights illustrate both the power and the limits of human understanding, showing how observation, logic, and imagination work together to illuminate the deepest questions. At the same time, the story emphasizes humility. There are aspects of the universe that remain beyond reach, whether because they lie beyond our observational horizon, occur at energy scales too high to reproduce, or exist in forms of reality unlike anything we experience. The very concepts of time, space, and causality may change when applied to the earliest moments. Some possibilities are likely to remain forever in the realm of theory, yet the pursuit itself is meaningful. Each calculation, each observation, each experiment expands the boundary of knowledge, connecting us in a direct way to the history of the cosmos. The act of understanding, even partially, allows us to participate in the unfolding story of the universe. From the first microseconds to the formation of elementary particles, quarks, and leptons, to the inflationary expansion that shaped galaxies, the universe's evolution is a tale of complexity arising from simplicity. Quantum fluctuations grew into large-scale structures, while gravity, energy, and matter interacted to produce the cosmos we observe today. Even when considering the pre-Big Bang realm, where time may not exist, and space is a quantum possibility, the laws of physics provide a coherent framework. Every observation, from the faintest microwave signal to the distribution of distant galaxies, helps anchor these ideas, giving them empirical weight. The story is scientific, precise, and yet deeply inspiring, connecting our human understanding to cosmic processes far beyond daily experience. Considering the multiverse and pre-Big Bang models emphasizes that the story of the universe may be far larger than we can see. Our Big Bang may be only one of countless beginnings, each unfolding according to its own dynamics. While these possibilities are speculative, they are constrained by mathematics, quantum theory, and cosmological observation. This perspective invites reflection on the nature of existence, the limits of perception, and the role of observation in shaping understanding. It highlights that even in the absence of direct evidence, disciplined reasoning allows humans to approach questions that are otherwise inaccessible, demonstrating the power of science to extend beyond immediate experience. As we synthesize what is known, a picture emerges of a universe governed by consistent laws, yet rich with possibilities. The Big Bang marks the transition from extreme early conditions to the classical universe, but questions of before remain open. Quantum fluctuations, inflation, and high-energy physics all contribute to the universe's earliest evolution. Observational evidence, from the cosmic microwave background to galaxy surveys, constrains theoretical models, while experiments at particle accelerators provide insights into fundamental forces and particles. Each line of inquiry reinforces the others, building a cohesive understanding that stretches from the quantum scale to the cosmic horizon. The picture is complex, but it is coherent, grounded in evidence, and capable of guiding future exploration. In quiet reflection, one can imagine the universe as an ongoing process. From timeless quantum states to inflation, particle formation, and the growth of galaxies, each stage follows natural laws that connect seamlessly. While the earliest moments are distant and often inaccessible, their consequences shape the cosmos we inhabit. The universe's story is continuous, unfolding independently of human observation. Yet our ability to reconstruct this history, to understand the principles that govern it, allows us to feel a connection to the vast expanse of space and time. Even in rest, the cosmos continues to evolve, carrying forward the story that began long before we existed. The final perspective is calm and reflective. Science provides a remarkable narrative, weaving together observation, theory, and reasoning to explain the universe from its earliest moments to the present. Yet it also acknowledges limits. Some aspects may remain forever beyond reach, while others will gradually come into view as technology and theory advance. The story of the cosmos continues quietly, regardless of whether we observe it. By understanding what is known, what is speculative, and what remains uncertain, we gain a sense of place in the universe. We are part of an unfolding history, able to witness and interpret its evolution, even while resting and contemplating its vastness. The universe's story is ongoing, immense, and beautifully ordered, stretching across space and time far beyond our immediate perception. In this way, we lie quietly, connected to a cosmos that continues its journey, shaped by laws that govern all that exists, and guided by patterns that extend from the first quantum fluctuations to the vast galaxies we see today. The story of the universe, from the earliest quantum events to the expansion and formation of matter, shows both what humans can know and the limits that remain. It emphasizes observation, careful reasoning, and imagination guided by evidence. While the earliest times, the pre-Big Bang possibilities, and the multiverse may remain partially speculative, the laws of physics allow coherent models and predictions. The cosmos continues to unfold independently, yet by listening, measuring, and thinking, we participate in its story. As we rest, the universe evolves, carrying the consequences of its earliest states, the growth of structure, and the emergence of complexity. It is a story of continuity, law, and possibility, extending beyond the limits of perception, yet accessible to the human mind through study, reflection, and understanding. In the quiet of thought or sleep, the universe's vastness is apparent. Its beginning, its evolution, and its ongoing changes are part of a continuum that stretches from the infinitesimal to the immense. Each galaxy, star, and particle carries the imprint of events that happened billions of years ago. Even as we pause, the cosmos continues to expand, to evolve, and to follow the laws that have governed it since the earliest quantum fluctuations. The story is both humbling and inspiring. It reminds us that the universe is larger and older than any single mind can grasp. Yet it is coherent, predictable in its laws, and connected in ways that allow humans to understand, explore, and appreciate its depth. This narrative concludes with a calm recognition that the universe moves forward, carrying with it the consequences of all that has occurred, while we rest, safely observing its ongoing journey.